I also welcome everybody. My name is Roland Kamaras, and the topic of this presentation will be the Locky ransomware. And this talk is about the anti-analysis techniques used by the ransomware. But before we delve into the technical details of the defense methods used by the ransomware, I want to tell a few words about me. I graduated from the Budapest University of Technology and Economics a few years ago in software engineering department. And at the MSc in the university, I joined to the Crisis Lab and its student core, and to the Spam and Hacks Capture the Flag CTF team. And now I work at the Hacktivity Technologies Kft. As an IT security specialist. And first of all, in this presentation, I want to speak about the Locky ransomware, and I want to answer this question: that what the Locky ransomware is, and I want to tell a few words about its spreading method, its distribution technique, and a short summary about its working method. And after that, I want to focus on the anti-analysis techniques used within the ransomware, and I want to focus on our analysis results. And at the remaining part of this presentation, I want to talk about a Hungarian ransomware called Locky, which is short for the Hungarian Locky. And I want to highlight the similarities and mainly the most significant differences between the Locky and the Hacky ransomware, because Hacky looks like as the Locky ransomware, but there are huge differences between the two ransomware families. And at the end of this presentation, I want to conclude the results of our examination. So let's start with a short introduction to the Locky ransomware. The Locky ransomware is a ransomware malware that is released in the February of 2016, and the ransomware itself is delivered by a phishing campaign using some kind of social engineering technique, and the ransomware itself using an email with an attached Microsoft Office Word document that contains malicious macros. So if the user opens the document and enables the macros within the document, the macros will then save and launch a ransomware, a downloader binary. And this will be the first phase of the infection. And this downloader binary will download the actual encryption payload, that is the ransomware itself, from a command and control server, a CNC server, that is controlled by the attackers. And after that, the payload is loaded into the memory of the user system and encrypts all files that match particular extensions on the victim computer. It is important to note that there are numerous versions, numerous variants of the Locky ransomware that are using different file extensions for the encrypted files, and the name of these versions will be the name of the extension that the ransomware uses when encrypting files. So, for example, Locky, Odin, Tor, and so on. And it's important that in this presentation I want to talk about the Tor variant of the ransomware that is originally delivered by JS, JavaScript, or VBS, Visual Basic Script attachment. And the ransomware itself is also active in 2017. And the most recent version of the ransomware is the Osiris. So the name of the most recent version of the ransomware is Osiris. It was released in the end of the last year. So a few words about the working method of the ransomware. As I mentioned, the ransomware itself encrypts all files on the user's computer with a specific extension, and after encryption, the message is displayed on the user's desktop. Here you can see an example for this ransom note for this message, and this message instructs the victim user to download a specific browser, a Tor browser, and to visit a specific cyber criminal operated website where the victim can find useful information to decrypt his or her file. Okay. The ransomware itself is a 32-bit Windows executable that contains the malicious core pegged and encrypted and, of course, obfuscated. And within the outer executable, there is an encrypted DLL. So the outer executable employs an encrypted DLL installer. And after unpacking the internal encrypted DLL, the executable dropper creates a new process from itself, spawns a new process from itself, and injects and loads the already extracted DLL into the newly created process, into the address space of the newly created process. And finally, passes the control flow to the entry point of the DLL. So after deployment, the ransomware runs its dropped copy, usually from the actual user's temp folder, and encrypts all files that have the specified extensions, as I mentioned earlier. The encryption is performed using strong cryptography algorithms, such as the RSA asymmetric key crypto algorithm or the AS symmetric key crypto. So, because the attackers possess the private key pair of the RSA key, it is practically impossible to decrypt the encrypted files manually. The sample communicates with the CNC server, with its remote CNC server, with a custom HTTP-based protocol using HTTP post requests, and the full communication over this channel is encrypted. And it is important to note that the public RSA key that is needed by the ransomware to encrypt the files and the ransom node and some other information are also fetched from this remote CNC server by the internal of the ransomware. But in the focus of this presentation is in the anti-analysis techniques of the ransomware. And here you can see the unique hash fingerprints of the samples that we have examined during our analysis. And in this presentation, I went to focus of the results of the analysis of these samples. You can see the MD5, SHA-1, and SHA-256 fingerprints of the examined samples. So it's important to note that the outer executable, the outer 32-bit executable of the ransomware itself uses a multi-layer defense method. And the first layer of its defense method is a Nusoft installer package. So the ransomware binary, and then this outer executable binary, is pegged into a Nusoft, a specific Nusoft installer package. So the installer package is used as a packing method, but as an obfuscation layer and the loader too. An obvious example for some strings in the binary that indicate that the ransomware uses the Nusoft installer package can be seen here. For example, the Nusoft in string, within the binary, the presence of the string in the binary, the presence of these strings in the binary, of course. The unpacking process of the binary is a very simple exercise. You can extract the binary using, for example, some kind of zip application that can extract NSIS packages. And after extraction, we get the following list of files. You see a plugins dir directory and some other files. The important thing is that most of these files are not important, are not relevant for us. They are just some component files of the installer package. The two important files for us is the NSIS.NSI file that contains script code, and another file that contains encrypted content, which has a random name in this example. And if we go into the plugins dir directory, there are further files. The only relevant file for us here is the system.dll file, which is a plugin of the NSIS installer package. And this module, this plugin, enables for the developers to invoke directly Windows API calls from the previous mentioned NSIS.NSI script. The purpose of the NSIS script is to describe the necessary steps, the necessary process to install the binary itself. And if we look into this file, into the script file, we can see the onInit function at the top of the slide. This function is automatically called within the script file when the NSIS installer package is executed. And the malware uses a very simple obfuscation technique as the first layer of its defense. It only includes a lot of junk code within the script code. And if we remove the instructions or the lines that is starting with the int-op instruction, the code of the script can be more readable. And another important thing is the system call function inside the script. The call function is implemented in the mentioned system.dll plugin, and using this call function within the script can invoke Windows API calls directly. The only parameter of the call function is the name of the Windows API call. And another obfuscation technique that is presented within the script is that the full name of this module, Windows API, the full name of this Windows API function or call is built up from substrings. An example, you can see an example for this, if you see the strcpy function in the third line of the script. And after we manually built up from the substrings the name of the Windows API call, after that, the decoded NSIS instructions will be the following. So we get the following code snippet. In the first line, the ransomware tries to retrieve the address of the kernel32.dll library, because when the process is running, the kernel32.dll is already loaded into the address space of the ransomware. So the only purpose of this function invocation is to retrieve the address to the actually loaded module. And after that, right after that, the script uses the catpos address Windows API function, which is again in the kernel32.dll module, and tries to retrieve the starting address of some kernel32.dll functions. For example, create file, virtual alloc, read file, and close handle. And the addresses of these functions, the starting addresses of these functions will be stored in R2, R3, R4, and R5 variables, or registers if we use the terminology of the NSIS installer. Okay, and if we look at the second half of the script snippet, and if we replace the register names with their values, we can get the following script snippet. And here we see that the ransomware tries to not tries to create, but tries to open the already mentioned file with random name from the root directory of the installer package. And then, using the read file Windows API call, it simply reads the content of this encrypted binary into the newly allocated memory area that is allocated by the virtual alloc Windows API call. And then closes the handle of the file. It's not important for us. And the important for us is the last line of this code. In the last line of the code, the ransomware invokes a specific address within the already loaded encrypted binary. because the starting address of this binary will be in the R0 register, and you can see an offset value after the name of this register. And it passes a single parameter to this code, which will be the name of this encrypted binary within the NSIS installer package. Okay, so from here, in the focus of this presentation will be the encrypted binary payload. And within the encrypted binary payload, multi-level XOR encryption is performed. As I mentioned in the previous slide, the NSIS script passes control flow to an executable code snippet within the encrypted binary, because not the whole binary is encrypted, but there is 3 lines of code that is clear. And here you can see the code that is not encrypted within the mentioned file. And here you can see an assembly trace, an assembly instruction trace. And if you look at to the first instruction, the first assembly instruction, you see a move instruction. This move instruction moves the 0xC3 value into the DL register of the CPU. And it's important that the 0xC3 value is the hexadecimal representation of the assembly ret instruction. So here the purpose of the assembly trace is to find within this trace the first ret instruction. And after it finds the ret instruction, it pops up from the binary the next 2 4-byte values. The first 4-byte value will be the length, will be a length parameter, and the next 4-byte value will be an XOR key. And this XOR key will be used to decrypt the remaining part of the binary, the remaining encrypted part of the binary. Okay. And after the decryption of the remaining part of the binary, the next instruction, the decrypted instructions, assembly instructions, after the length and an XOR key parameter, will be the second stage of the decryption routine. And it is important that the second stage of the decryption uses totally the same instructions that were in the first stage. And the bad news is that the ransomware employs further 6 layers of decryption. But the good news is that all decryption layers contains the same instructions. So the binary performs a total of 8 layers of decryption, and the only difference between the stages is the value of the decryption length and the value of the XOR key parameter. And after the last layer of decryption, the control flow continues at the beginning of a C function after a jump instruction, but it is not necessary as. Okay. So, as I mentioned, the final malicious payload is an embedded and encrypted DLL inside the executable. But this DLL is encrypted now, and this DLL is inside this encrypted binary blob at the start of this encrypted binary blob. And right after this encrypted binary blob will be the assembly trace that I saw. Okay. And the next layer of the next layer of the malware defense method further obfuscation and encryption in the executable binary, and the malware after this assembly trace essentially performs the following tasks. Build some kind of import address table that is used to refer the necessary external library functions, primary from kernel32.dll and from ADV API 32.dll. and the binary tries to find the specified functions within these modules, within these loaded modules, based on their export table based on the function's specific checksum value. And the ransomware tries to find the appropriate function based on this checksum value. The ransomware, it is important that the ransomware uses a modified version of the CRC32 checksum calculation algorithm. And after it finds the necessary import functions from the kernel32.dll and ADV API 32.dll modules, then it fills the already mentioned import address table. Here you can see the manually imported functions of the ransomware itself from the kernel32.dll and ADV API 32.dll modules. Okay, and the last and the next step of the unpacking method that is applied within the ransomware is to extract the DLL and decrypt the DLL from the encrypted binary. So the process of the executable, that is the NSIS installer package, and its process loads the originally encrypted binary image of the ransomware. This will be the file that I mentioned with random name. And this file embeds a malicious encrypted DLL at offset 0x11. And from this offset, the encrypted DLL will be placed, the encrypted binary blob of the DLL will be placed within the binary, and the DLL is XOR decrypted. So the DLL is decrypted using a simple XOR algorithm that we will see in the next slide. And the length of the decryption and the XOR key is stored right before the encrypted binary blob of the DLL. Okay. Oh, sorry. The XOR key is not stored right before the encrypted binary, but the Unicode string of the file name serves as the XOR key of the decryption. That's correct. Okay. And here you can see the XOR decryption routine. It's a simple XOR decryption. The algorithm goes through the embedded and encrypted binary blob and the actual 4 bytes of the binary blob is XORed with the 4-byte XOR key, and the resulting key is further and the resulting value is further XORed with an offset parameter that will be the value of the index parameter in our case. Okay, and as the last step of the unpacking process, the original process spawns a new process from itself using the NSIS installer package, and it spawns the process in suspended state. And then the embedded DLL is manually loaded and relocated. It is important that the binary contains relocation of instructions using the standard Windows PE relocation table format, and then the DLL is injected into the address space of the newly created process using a shared memory between the original process and between the newly created process, using two anti-DLL.dll functions, namely the anti-create section and anti-mapview of section functions. So the malware creates an allocated memory within the original process using the anti-create section, and using the anti-mapview of section, the ransomware maps this memory area into the address space of the newly created process, and then simply copies the content of the decrypted DLL into the address space of the target process. Okay, an interesting feature within the ransomware that the anti-DLL functions, as I mentioned, are not called directly from the anti-DLL.dll module. The binary directly invokes the appropriate system calls that are related to the actual anti-DLL functions. And to achieve this, the ransomware determines the appropriate system call numbers based on the code, based on the instructions of the mentioned anti-DLL functions. And this is done most likely to make it difficult the automatic analysis of the ransomware, and maybe to be hidden from detection. And the last step, in this phase of the injection, the DLL is injected into the address space of the target process, but the control flow is not passed yet to the entry point of the DLL. So the last step of the injection is to hijack the control flow. And in order to do this, the original process modifies the value of the image base address, some kind of meta information within the suspended process to the base address of the injected DLL. And then hijack the control flow of the suspended process to the entry point of the DLL by exchanging the value in register AIX of the CPU, because this register, right after loading, right after the load has been loaded the binary, the register AIX contains the address of the entry point of the executable. But it is important that it can be done directly in modern operating systems. So a process can't directly exchange the value in any of the registers in another CPU, in another thread context, in another process. So the ransomware itself uses a simple trick, or a standard method. The original CPU context is saved by the ransomware, and then it exchanges the value within the AIX register to point to the entry point of the DLL, and then restores the CPU context within the target process using standard Windows API calls, and then resumes the newly created process, so it will execute after its suspended state. Okay, as I promised at the start of this presentation, I want to talk a short about a Hungarian ransomware called Hacktivity, which is the abbreviation of Hungarian Locky. And at the first glance, this ransomware family looks like the Locky, but if we look at the ransomware closer, we can see that there are huge differences between the two ransomware families. So here you can see the unique hash fingerprints of the examined samples, SHA-1 fingerprint. Okay, here are the three similarities between the two ransomware samples. Both ransomwares aim is to encrypt valuable files and to demand money for the decryption. The encryption process is quite similar in both cases. AS keys, randomly generated AS key is used for file encryption in both cases, and this randomly generated AS key is then further encrypted by a public RSA key. And at the end of the encryption process, the victim machine looks similar in both cases. In this picture, you can see an example for the case of the Hacky ransomware. Okay, and the differences between the two ransomware samples, the main and most significant differences that indicate that the Hacky ransomware family can be created by the same threat actors that Locky. Okay, so the most significant difference between the two ransomware samples is the programming language. Locky is implemented in C language, while Hacky uses and based on Microsoft Visual Basic .NET. So it uses managed code, and it is implemented in Visual Basic script. Hacky's code uses Hungarian words as namespace and method of variable names. Another difference is the public encryption key. Locky retrieves, and the retrieving method of the public encryption key. Locky retrieves the public RSA key from a remote CNC server that is controlled by the attackers. In the case of Hacky, the public RSA key is hard-coded. It's hard-coded in XML format. And an interesting thing in the Hacky ransomware is that all the examined samples contain the same hard-coded RSA public key. Hacky displays a dummy Word document while encrypting files, and after that performs a system restart. In case of Locky, this activity is not in the binary, is not implemented in the binary. Another difference is the payment requesting method. Locky instructs the user to visit Tor pages. In case of Hacky, Hacky requires victims to send an email to the given mail to Tor address. Here you can see a code snippet from the decompiled source code of the Hacky. The comments are placed by us. And here you can see the Hungarian words in variable names or in object names and in the names of the functions. So, as the conclusion of this presentation, I want to tell that in case of the Locky ransomware, we saw that this ransomware is not using any new technique, any new trick. Rather, it's using well-known, quasi-standard techniques. But the quantity of the techniques used in the ransomware and applied in the ransomware indicates that the authors invested sufficient and significant effort to hide the internal working and internal malicious functionality of the ransomware itself. Maybe this is done in order to make difficult static analysis of these samples and the reverse engineering of the samples, and also to harden the analysis in automated sandbox environments. And we saw from the example of the Hacky ransomware that other threat actors usually try to copy the behavior of successful ransomwares, maybe in order to increase their chances of getting ransom payments from victims. So that's it. Thank you.